Welcome to the lecture 4 of Python and matrices course. The subtopic for today's lecture is vector and matrices part 3. So we will be still continuing and discussing concepts related to vectors and matrices, and we will do some important operations on them. First, we will begin with some basic operations like dot products and cross products of vectors. Then we will deal with some common operations of matrix addition, transpose, and so on. And then we'll deal with an important topic, which is solving a set of linear equation using matrices. And in that context, we will also define the inversion operation. And finally, we will finish with the rank computations of a given matrices. So let's get started and let's begin with some vector operations. So the first vector operation that I want to talk about in today's class is related to the concept of dot product. And essentially, the dot product is sum of the products of the corresponding entries of two different vectors. So when we say a vector A is dotted by B, and that is denoted by this point symbol, is essentially given by this equation summation I equal to 1 to n AI BI. In order for this operation to be valid, first thing that you need to note at that is that the dimension of the dimensions of the vectors are essentially going to be same. If you have same dimension vector, then this operation is meaningful. Okay, so let's take an example and let's see how we can compute the dot product of these two vectors A and B. So here you can see we have a vector which has 4 tuple A and a vector which has 4 tuples in B, and they have different entries in different location. If I want to take a dot product of these two vectors, how do we go about that? The simplest way to understand is corresponding elements. So if I take this 2 and if I take this 1 and if I multiply them and create this 2 times 1, right, that will be the first element of the resultant. That's the first element that we want to compute. Then we take 4, 2, and that will be 8. And then similarly we take minus 1, 1, multiply them, that is going to be minus 1. We take 8 and 5, multiply them, that will be minus 40, and we add them together. So essentially what we are going to do, we are going to take this corresponding elements, multiply each of the elements together, 2, 1, 4, 2, minus 1, 1, 8, and minus 5, and then add them together. So if we add them together, we will basically get this equation, and that is essentially what we are implementing this equation form numerically. That's what is being done here, and this turns out to be minus 31, and that is essentially the dot product of vector A and B. The first thing that I want to notice is that the dot product of two vectors is only giving you magnitude, and there is no direction associated with this product. So the dot product of two vectors essentially results in a scalar, which is a single value which has no sense of direction, and that is something you may want to note with respect to the dot product. But still, it's a good idea to understand the intuitive and geometric meaning of what the dot products are. And essentially the idea is, like, let's say if you're dotting two vectors, let's say vector A by B, then what you do is you take vector B and you project that vector B on A, and that projection will have a length. You take that length and then you multiply that with the length of A itself, and that magnitude of this projection of B on A and multiplied by the length of A itself is the geometric meaning of dot. So let's dot product. So let's take these examples forward. Let's take some geometric examples and see how we can carry what does this mean. So let's say we have this grid which we are using, and let's say we have a vector A which is given by this line here, and let's say we have a vector V which is given by this 0, 3. So vector V is 0. So what we'll do is we'll take this vector B, we'll project it on vector A. So this will be the projection. So we take the magnitude of that and then the magnitude of the overall A, and we multiply them together. Okay, so let's see how this looks. So we are taking the B, we have projected the B on A, and the length of projected B on A is essentially this much, right? So we take that, and that will be the first component here. Okay, so that will be the first component, and then we take the length of the overall vector A itself, which is this, right? That will be the second component of this multiplication. Okay, and when we multiply that together, that will result essentially in a value which is basically representing the dot product of vector A and B. Now, there are signs associated, right? Typically, when the vectors, two vectors are pointing in the same direction, their dot product is positive. When they're pointing in opposite direction, their dot product is negative. When two vectors are perpendicular, there will be, if you project in that case, the projection of vector B on A is going to result in 0 length, and that's why that dot product is going to be 0. Okay. So these are like some of the scenarios where you can have different cases of positive, negative, or 0 dot products. Important thing to note that dot product results in a scalar value and it does not result in a vector value. So let's move on to the second vector operations that is important, which is known as the cross product of two vectors. Now it turns out the cross product results in a vector. It does not result in a scalar. So that's the main differentiating thing. It's essentially a vector that is at right angle to the both the original vectors A and B. So if I take these two vectors A and B, the dot product, let's say C of A cross B, will be perpendicular to both A and B. Okay, so I take this vector is going to be 90 degree with respect to A, and this vector is also going to be 90 degree with respect to vector V. So that's one thing that need to do. And the second is that the magnitude of this vector, what is the magnitude of this vector, is essentially depends upon the area spanned by A and B vectors. So let's see this illustration which explains this idea. See, if I take this vector and expand and create this parallelogram, right? This parallelogram is going to have an area, and that area essentially defines the magnitude or the length of A cross B. Whereas the direction is essentially it's 90 degree to A, 90 degree to B, and that's the direction of A cross B, but the magnitude is essentially the area of the parallelogram. Now, turns out, this area of the parallelogram is essentially obtained by taking the determinant operation, and this is something that we discussed in the last class. So if you take A and B, and if you take the determinant of that, that gives the magnitude of the A cross B. Okay, so two things are needed for vectors, which is the magnitude and the direction, and A cross B results in a vector, so that's why you need an area computation and we need a direction computation, which is denoted by, it has to be by constraint that it has to be perpendicular to B and it has to be perpendicular to A. Okay, so let's see how this is actually connected with numerical aspects. So this is the geometrical meaning of what cross product is, and essentially the determinant here is determining the magnitude of A cross B. Okay. So the direction of A in B is also important, and let's discuss how that is done. Right now, it depends upon, and we have already discussed right hand rule in the previous lectures too. It's right hand thumb rule that we use. Okay, and if A is on the left of B, then A cross B is positive. Okay, and if A is right of B, then A cross B is negative. So, depending upon the orientation of A and B and their respective thing, this direction could be positive or negative. Okay. Now, we discussed some geometric aspect about what cross product means. Let's see how can we numerically implement a cross product in an efficient way. Okay, so the standard formula for cross product of two vectors A and B, which has, let's say, multiple tuples, for example, 3 tuples A1, A2, and A in A, and B1, B2, and B3 in vector B. If I want to take a cross product of that, then essentially that could be given by this equation. What I do, I create a determinant where the first column is I, J, and K unit vector. The second column is essentially the A vector. The second column is essentially the B vector. Now, if I create a matrix and take the determinant of that matrix, that will essentially help me in computing the cross product. So if I simplify this and do the determinant of this matrix here, then I have this equation, and this is the equation that will be used to compute A cross B. Okay. So A cross B is another vector, right angle with A and B, and its position is defined by the coefficients of I, J, and K given by the set of equations that are given here. So let's take a numerical example and try to understand what this computation means. Okay. So here is an example that I have two vectors U and V, and I want to take a cross product of U cross V. Remember, this vector does not have jth component, so what we can do is, in order to write this equation, we can say that the jth component of this vector is 0, right? So if that is the case, then what I can do, I can do u cross v, which means essentially 1, 2, minus 2, 2, and the jth is 0, so that would be the second element, and k is 1, that's why we have 1 here. Okay, so that gives me this operation. This is the operation that I need to do, but how is it implemented? We need to be basically determining the determinant of this I, j, k, 1, 2, minus 2, 2, 0, 1. And when I compute this determinant, I will get this simplified version, which is I 2 minus 0 minus j 1 plus 4 plus k 0 minus 4. And if I simplify this further, I will get this vector, which is 2i minus 5j minus 4k. And this is essentially the cross product of u and v. And now note that this is a vector. Okay, it has a magnitude and it also has a direction. So this is some important concept with respect to the numerical implementation of the cross product of two vectors, and also some geometric intuition what it essentially means when we are taking the cross product of two different vectors.